All right, so before jumping into the technical details, let me set the stage by describing the context of where I'm coming from. So I'm from the automotive domain. We are mostly developing a platform for autonomous driving. And we have some requirements that are very specific to our use cases that we need to describe before jumping into the solution space. So the first requirement is that we have strict safety requirements. Autonomous driving, it's clear if you detect an obstacle and do not evade in time or not at all, clearly people will be harmed. So we have strong requirements both for software safety as well as system safety. A related aspect is strong separation of concerns. So we have mixed criticality systems. We need to make sure that the infotainment application does not interfere with our autonomous driving application. And also we do have an environment where we have many suppliers contributing to the overall functionality. And no supplier wants to be packed with another supplier into one process, because then testing gets really problematic. So for all of this, we also need a very high level of offline analyzability. We need to generate evidences that the system is working as it is supposed to. And we have to guarantee deadlines, meaning it's a hard real-time system. So a system is only safe if it is guaranteed to be functionally correct, but also provides the output in a bounded amount of time. So this is important here in the sense that there are multiple definitions of what real-time means. So the control guys mostly mean very high frequencies, very low latencies. In our case, this is not really the case. The timing can be in the area of hundreds of milliseconds, but we need to guarantee that an output is there before a given time passed, right? So you see the obstacle, you need to evade it, you need to apply your steering commands fast enough. And all of this needs to be analyzed and reasoned about. And this pipeline here looks quite simple and nice, but the reality is that the processing actually looks more like this. So this is a highly connected graph with a high level of parallelism there, and just making it run and test and see whether the timing is okay just does not work. So we need a better approach. So what we are now aiming for with this real-time data flow approach is we want to have a defined and predictable execution behavior. We don't want chaotic executions. We want this to be more easily analyzable with less, let's say, complexity in it. Also, we need to have stable and predictable end-to-end latencies. So this processing chain must finish in 100 milliseconds or whatever the deadline is. And we need to make sure that we can really have this when it's running. As I already said, we do have this application distributed across multiple processes, so we need to coordinate across them in a way that makes it usable. And in the end, we also need to control the system when the temporal behavior does not match our expectations, because an algorithm can run longer than expected. There could be temporal interference. We cannot provision a system to the worst case execution time of a application when it's running on a multi-core setup where there's lots of interference going on. So what's the issue, right? The weakness with ROS. So one of the issues is it's completely data-driven. In the sense, processing starts as soon as data is there. This is nice. The whole processing is triggered implicitly in the overall system. But the problem is if the data arrives very late, the whole processing is delayed. Right? So we need some way to control this real-time progress to make sure that we get an output out in the time we need. And another thing is that N-to-1 communication is not properly supported. So you can work around this by installing a callback to multiple subscriptions, but then you need to deal with concurrency and aspects like that. Or you can set up timers, which could be a workaround for both problems, but they introduce indeterminism, because what data is there when the processing happens is different all the time. And as the colleague before me said, when you test things, you do not want flakiness. You do not want to have it passing one time and not passing the other one. So how would we now change ROS to make it data flow capable? So the one thing is we are not supporting the full functionality because we don't need it. So in the sense, For communication, we only support topics. Communication is strictly unidirectional. And most importantly, we have an explicit dispatching. So we do not just let the system run and dispatch things in a chaotic way, but we want to explicitly control this. So how does this now overall work? So briefly regarding the process, how would this system now be developed? During development, we create a mapping between callbacks and the topics they subscribe to and publish. So not on node level, but really on callback level. During initialization, we collect this information from all processes out there and build a directed acyclic graph of the overall system. And at runtime, we execute through this in an explicit fashion. So what does this mean? If we take this example here, this first callback finished, we see that callbacks 2, 3, and 4 depend on callback 1 and only 1, and therefore we can allow them to execute. However, if we go on and we have callback 4 finish, we cannot yet dispatch the callback 8. Why? Because it also depends on callbacks 3 and 7. So what's the difference now? We're not going to do anything in callback 8. We're not context switching to it to store data, to trigger an execution, which we then immediately figure out we do not yet need to do anything yet. So we just dispatch the other callbacks first, and we get to 8 as soon as all its predecessors finished. And this allows us now to add a few extensions to this. So one extension here is data flow scheduling. So because we explicitly control the dispatching of the callbacks in the system, we can add logics. And here we would just add timing annotations to each callback. So in this example here, each callback takes 10 time units. So this could be like milliseconds or whatever. And we can use this information to control the system execution in a way to optimize this end-to-end latency. So because what is the issue here? If we again take the example of callback 1 finishing, we have 3 callbacks that could now be dispatched, but we might only have 2 cores available, right? And therefore we need to choose 2 callbacks and one will just have to wait. In a normal ROS2 system, it would just be kind of random. However, the operating system scheduler is configured, 2 of them will fire first, right? Because maybe the data is there first, or maybe the scheduling priorities are configured accordingly. But we want to do this explicitly and derive priorities for those. Why do we want this? And here there's a trace. Let's not go through it completely, but seeing just on a high level, we have 2 choices. Either we dispatch callbacks 2 and 3, and then we get to an overall processing of 40 time units in the worst case. Of course, those callbacks could run faster, but let's say the worst case is then in total 40. However, if we dispatch callbacks 3 and 4, the overall time will be 50 time units. Why? Because in the step 2, when callbacks 3 and 4 also finished, there's only one ready callback in the system that can be executed, and that's this callback 2. This means we will have 1 core that is not used at all because there's nothing to run, and therefore the overall processing time will be longer. So this means we can add now scheduling heuristics. We will never be able to have an optimal schedule in here because scheduling is NP complete. It's not possible to find an optimal solution, but you can have heuristics that optimize the behavior in a way that it's definitely better than just randomly dispatching things. Another extension is timeout handling. So if we take the left graph, if callback 3 takes longer, the whole processing will take longer, right? I mean, this is the problem in ROS2 already, but it would also in the data flow approach be a problem if we used 10 time units, but in reality it takes 100 time units, right? It will just take longer, so the scheduling does not really help, so it will be delayed. So what we do instead is we introduce a timing supervision mechanism, which is set up when you dispatch a callback, and we look at the timing annotation, we say, okay, this callback has 10 time units available, so we will trigger in 10 time units, and check whether this callback has finished or not. And if it has not finished, we just stop it. In a sense, we kill it or we do something more graceful, but we prevent it from continuing execution. And for the overall processing, we just consider it like finished, right? So what does this mean? Even though this callback is now not producing data, we will eventually dispatch callback 8. It will have data from those callback 7 and 4, right, but not from 8. But we have guaranteed forward progress. So the callback needs to be able to deal with not receiving this data. It needs to be either able to still compute things, or it can, I don't know, abort, raise an error, whatever is useful in the application context. But the overall processing will be time deterministic. So we will guarantee that in 40 time units, we process everything. Of course, I mean, if this timeout now happens to all callbacks, nothing properly will still happen. But if we say those timeouts happen not too often, we can guarantee this here. So what does this mean? This means in the first setup, where we don't have this timing handling, the overall system is not time deterministic because it will take a random amount of time to execute, but it is fully data and data flow deterministic. So the data in and to the data out is always the same, and the execution order is also the same. In the second case, we are data flow and time deterministic because we still dispatch everything in the order it is supposed to run. And it has a guaranteed overall deadline, but it's not data deterministic because some callbacks don't get data, so the outputs will, of course, differ a bit in each time this happens. But the good thing is we know this, right? Because we see this timeout, we can write a log, we can write an error message. We know that this happened. It's not like random and we don't know what was going on. We see, okay, there was a timeout, there's no data, and this data matches here. This is also helpful for testing purposes because we can just test all of those scenarios of callbacks taking longer by just setting a very low timeout value, right? Just make it timeout in a few microseconds. You can test this behavior quite nicely. So enough theory. How we implemented this in a proof of concept, and the architecture looks like the following. So in each process, we have a data flow executor, which does normal executor stuff. It triggers those callbacks, and they are all coordinated by the central data flow scheduler. So at startup, when we build up the system, the data flow executors collect this mapping of callbacks and published and subscribed topics, communicate this to the central data flow scheduler, which builds the graph of the overall system, and at runtime, it dispatches the callback according to those graph precedence constraints. How does all of this work? The scheduler is triggered iteratively by a timer, cyclically, for example. In the first step, we determine all callbacks that are ready. If we have some, we check the priorities of those callbacks and then trigger as many callbacks as we have cores available. We signal this to the data flow executors where the callbacks are located. They dispatch the callback, they set up the timing supervision, the callback runs, and once it's finished or at timeouts, we signal back to the data flow scheduler to update the graph state, and then this repeats until we have iterated through the whole graph, which means that we have no ready callbacks anymore. We reset the graph state and the iteration, and will be triggered again later on. So how would you use all of this? It is, I think, relatively straightforward. So if you look at our main, we basically define our topics that we subscribe or publish. We set up our node. But additionally, we also configure this callback info vector. And there you basically just say, OK, this is the function pointer to my code to execute. Those are the topics that it needs, that it subscribes to. Those are the topics it publishes. Should there be a timing supervision or not? What type of supervision are we using? What is the timing annotation we want to use? Then we spin up the executor, and again, the data is transferred to the scheduler, all of the graph is created, and we wait for triggering. The callbacks itself, as a first step, just need to read the topics they subscribe to, then they do the processing, and at the end, they publish the data they have. So I think this is a pretty reasonable design approach. So one thing was latencies. So again, the goal was not to have super minimal latencies. This is not the goal, but we want to have predictable latencies. And one thing we were still concerned is that this data flow scheduler is in the critical path of the processing, right? Normally the decision what to dispatch just is taken without any thought. It's just happening. So this is of course super fast. We here have this logic in the critical path, which could increase the latency. But we tried it out with the auto reference system. We had to adapt it a bit to fit our use case. So we have each node in a single process. We had to set different crunch values for the callbacks to make the scheduler work properly. And yeah, we measured the end-to-end latency. And you see the results here. The blue one is the ROS default, where in like the 2-core case, we have a latency of 125 milliseconds and quite some jitter, as you can see. And in the data flow approach, we have like 2 figures. The first one is random, where we disabled the scheduling logic. So this is really just triggering things in the right order without taking a conscious decision of what to dispatch next. As you can see, the performance gets already down to 45-ish milliseconds. And then we have the data flow scheduled approach, where we implemented a scheduling heuristic to optimize the dispatching in order to optimize it. And here we see another improvement. It's like 5%, so it's not huge. But there are 2 things to keep in mind here. First, it is only optimizing the computation part, right? So data transfer or the stack handling cannot be improved. So it's only the compute part. And the second thing is that this depends on how this graph looks like. So we did some simulations with different graph structures, and we had results that showed that the speed up is typically in the area of 5 to something like 15%, something a bit more, sometimes a bit less. But yeah, depending on the graph, this will be different. And for the AutoWare example, this is what we get. What you also see when we go to more cores, it is already quite optimal in this 3-core case. Yeah, ROS is still improving if we add more cores, so it's still not where we are yet. So to conclude, what are our main results? The data flow approach allows us a more deterministic and predictable runtime behavior. So there's not executions triggered kind of randomly, but we control this. We are fully data flow and data deterministic when we just let callbacks run until completion, but we can guarantee forward progress for when real-time requirements in the field are needed, and we can transition between easily. We can add additional logic to this, as we saw with 2 examples, but more things are possible. And yeah, for lessons learned, one thing that might be important here is asynchronous data handling is a kind of a problem because the DDS receive thread runs asynchronously. So sometimes we trigger a callback even though the data is not there. So some optimizations there would be needed. Next steps, obviously we can add more features. Another thing is performance optimization. So this is still a proof of concept. And it's in the critical path, so this will help. But the most important part for us is that we want to discuss general usability for the ROS2 community and see how we could contribute this. And with this, I want to end the talk. And if there are any questions, I'm happy to take them.
So we just have time for one quick question. Please, go ahead.
Okay, yeah. Thanks a lot for your talk. I really liked it. I was wondering this function where you recalculate the graph in the executor loop, how does it scale if you have many more topics and many more nodes?
So yeah, so computing the graph, it's graph theory, so this is kind of complex, but we do this only at init once. So it's really, really fast computing this graph. I don't have a concrete value for you now, but we're in the milliseconds range on a normal computer. So.
Okay. Thank you.
All right. Sorry for that, but time's up. Let's thank the speaker again.